Hello, I am Rohan Sarkar, a PhD student at Purdue University. I am delighted to present our work on Shape of You, precise 3D shape estimation for diverse body types. This work was done as a part of my internship at Amazon. Our goal is to estimate body shape and pose. For this, we fit SMPL body models to monocular images, which give us the pose and shape of the person in the image. Current methods, as you can see in the green SMPL meshes shown on the left, only work for certain body types that are dominant in the training data, but does not perform well on all body types, especially high BMI body types, which are usually underrepresented in the training dataset. In this work, our goal is to estimate precise 3D body shape and pose for diverse body types. Before we present our method, I would like to start with a brief introduction to SMPL and prior work. SMPL stands for Skinned Multi-Person Linear Model, which is a vertex-based parametric model that accurately represents a wide variety of body shapes in natural human poses. It is parameterized by phi that controls the global 3D position and orientation, shape coefficients beta that controls the body shape. As you can see in the figure, by changing the beta parameter, we can represent a wide variety of body shapes. And by controlling the theta parameter that controls the axis angle rotations, we can change the pose. SMPL is supplied with a linear blend skinning function SV, which generates a set of vertex positions V of a 3D mesh. There are two types of approaches that have typically been used in prior work to fit SMPL meshes to monocular images for estimating pose and shape. These are optimization-based and regression-based methods. On one hand, optimization methods like simplify iteratively fits the SMPL mesh to a sparse set of 2D joints, and on the other hand, regression-based methods like HMR directly regress the camera and SMPL pose and shape parameters. During training, they minimize the error between the projected joints from the predicted mesh and the annotated joints. We present another method, spin, which is a hybrid approach that combines the two types of approaches. It combines a prediction module like HMR and an iterative module like simplify. It is trained in two stages. In the first stage, the CNN predicts an initial shape which is not perfectly aligned. In the second stage, the refinement module is incorporated inside the training loop and refines the shape, as you can see in the figure. The refined shape is then used as pseudo ground truth for training the CNN in the next epoch. During inference, only the trained CNN is used to directly predict the SMPL parameters. A major drawback of previous approaches like spin is that they focus on improving pose but not body shape. As you can see in the examples, spin aligns the joints pretty well and hence the pose estimates are good. But spin cannot predict the body shape accurately. Our goal is to adopt spin's hybrid strategy but focus more on improving shape estimation both in the prediction and the refinement stages. A straightforward way to improve body shape estimation is to collect 3D body scans of people. However, this is expensive and time-consuming, and hence difficult to collect 3D ground truth for a diverse set of body types. However, collecting 2D data is relatively much cheaper, and this allows labeling much larger in-the-wild datasets comprising of people with diverse body shapes. Prior work uses a sparse set of 2D joints or open pose key points, which work well for certain body types, as shown in the bottom left. However, as one would expect, if it would not work for all body types as shown in the example on the bottom right, as the 2D points would not provide much shape-specific information. Some prior methods have used body silhouettes to accurately recover body shape. This works well for 3D animal reconstruction and people wearing skin-tight clothes. However, for such silhouette-based methods, only the boundary of the silhouette guides the loss, and often human clothing corrupts the silhouettes, as you can see the examples on the right, and hence body shape cannot be estimated correctly. A recent method, Shapey, collects body measurement data such as height, bust, waist, etc., and textual description of body types such as long legs, skinny, short, pear-shaped, and use them for training. Our goal is to improve shape estimation for diverse body types. The key insight that we use in our work is to use models that are trained using dense 2D ground truth to supervise 3D shape estimation. In our work, we show that extracting dense labels from dense pose provides a much richer shape-specific signal than sparse 2D joints and silhouettes. We will explain this with an example. For this image, we first run dense pose that aims at mapping all human pixels on a RGB image to the 3D surface of the human body. Since only pixels of the body have 3D SMPL correspondences, the dense model learns to estimate the body shape under the clothing. For each pixel, we find correspondence points on the 3D SMPL mesh as shown by the red dot. We can continue this for all the pixels in the foreground for the person and get dense correspondences. We show 5 such points in this example. In our work, we propose a dense correspondence loss that promotes alignment between a dense set of per pixel mesh to image correspondences, and this is defined by the equation at the bottom. So our training framework is a hybrid approach like spin network we saw before, but we focus on improving body shape estimation both in the prediction and refinement stage. Let us now go through our framework step by step. For an image I, we feed it to the CNN regressor to predict an initial mesh G. We then get the dense pose D, and we input the predicted mesh and the dense pose to our shape refinement module. The shape refinement module iteratively fits the predicted mesh to the dense correspondences using L iterative loss. As you can see at the bottom, the refined mesh G hat is then used as the ground truth to supervise the CNN regressor in the next epoch using another loss, L regression. Now we show some examples of how the body shape is refined during training. In the first 2 columns, we see the image and the corresponding dense pose. In the left SMPL, we see the initial prediction, and in the right, we see how the mesh is iteratively refined. Here is another example, and it can be seen that the refinement fits to the body shape under the clothing. And we show yet another example. We also introduce another loss named pose invariant vertex alignment loss. For this loss, we first project the predicted mesh in the T-pose, where phi t and theta t denote the global orientation and pose parameters in the neutral T-pose, and beta is the shape parameter predicted. Similarly, we also project the refined mesh in the T-pose. The only difference is in the shape parameter, which is denoted by beta for the predicted mesh in T-pose, and beta hat, which is the body shape coefficients for the refined mesh. We then use the linear blend skinning function SV to generate the vertices. The proposed loss penalizes variations between the predicted and refined mesh vertices in T-pose, that is, after the pose effects are removed. In our training framework that we showed earlier, we trained in 2 stages with 2 losses, L regression for training the CNN and L iterative for iterative refinement. We will now elaborate more on these 2 losses. In the first stage, we train the CNN to regress SMPL parameters using the regression loss, which is the sum of 3D and 2D joint alignment losses and mesh alignment losses. Among this, L3D joints, L2D joints, and L mesh were previously introduced in SPIN. In this work, we added the pose invariant vertex alignment loss for improving shape estimation. In stage 2, we use the iterative loss to refine the predictions made by the CNN iteratively using our shape refinement module. The loss L priors was used in SPIN to avoid unrealistic pose and body shapes. We added the dense correspondence loss that we explained earlier to refine the body shape. We then use the refined predictions to supervise the CNN in the next epoch. During inference, we use the trained CNN for prediction. Also, for body types that are underrepresented in the training data, we run another pass of energy minimization with loss L-iter to refine the test time predictions. The stage 3 refinement is optional. For training our network, we first pre-train on spin training datasets and fine-tune on the model agency dataset that was introduced by Shapey. However, we pre-compute the open pose joints and dense pose maps and use them, and do not use the body measurements and texture description that Shapey uses. We evaluate on the SSP3D dataset, which has 311 images of sports person with diverse body shapes. The metrics used are mean per vertex error in neutral T-pose. The lower the error, the better, and mean IOU between the predicted and the ground truth silhouette. The higher this metric, the better. We now show some qualitative results on the SSP3D dataset. The green SMPL meshes are generated by Shapey, and the pink ones are using our method. From table 1, we observe that using our full method, we have an overall improvement of 17.7% on per vertex error metric over Shapey. We conduct an ablation study and observe that the proposed T-loss improves performance of a network by 2.6%. Shape 3 refinement during inference improves performance further by 17.3%. And we perform on par with Shapey without the test time refinement and without using any of the linguistic or body measurement labels. Here are some qualitative results on diverse set of body types in different types of clothing that we downloaded online. The green meshes are those by Shapey, and the pink ones are using our method. Here are some more examples. In summary, we propose shape-specific loss functions to improve quality of 3D reconstruction on diverse human shapes, and we introduce two such losses. The first one is dense correspondence loss that promotes alignment of per pixel mesh-to-image correspondences, and T-pose loss that promotes vertex alignment by disentangling pose effects. We also add a refinement step during inference, which further improves shape estimation, particularly for body types that are underrepresented in the training distribution. Thirdly, our full method improves by 17.7% over Shapey on the SSP3D dataset without using any body measurements or semantic attributes for training. Thank you.